can we understand what are the different orbital habitats, understand the environment of these habitats in terms of the fields, external fields, gravitational, charged particle, all these things, and then say, okay, now if we have different species of objects, rocket bodies, CubeSats, this sort of stuff, how are these things going to behave based on the type of object they are and the habitat that they reside in, much like animal populations and that sort of stuff. Nobody's developed that before. So that's one of the things that we want to be able to develop. And I think that's going to help inform us of how these individuals of these different species in these different habitats actually behave long-term. What's the long-term evolution of these different species in these orbital habitats? Which ones are nomads? You might have some that, due to these perturbations, migrate from these low Earth orbits to these higher Earth orbits just due to these natural perturbations. But we don't know that exactly because we keep on modeling everything like it looks like a sphere and all this other stuff.
We're back with another episode of the Cold Star Project, this time with Moriba Jah. He is kind of a superhero when it comes to math and navigation. Been waiting a while to have him on, so I'm really excited to have him here. You may recognize these names. He has been the navigator for the Mars Global Surveyor, Mars Odyssey, Mars Express, Mars Exploration Rover, and the Mars Reconnaissance Orbiter. And he's a member of a whole lot of things and has received a lot of recognition and awards and that. So thanks for being here today.
Oh, thank you very much. It's an honor to be here.
You bet. Well, let's talk a lot about math. I really wanted to have a technical discussion with you because you are really into this stuff. You are at Texas University and building this Odin Institute into what looks like you want it to be a powerhouse of innovation and a resource for people to come to from all over the world to work with on space programs and that. So maybe tell us a little bit about that to start off with.
Yeah, so one of the things that I've been looking at, so I've been looking at this idea of space debris and space situational awareness since about 2006 when I left NASA's Jet Propulsion Lab and worked at the Air Force Research Laboratory. I spent 5 years on Maui using the telescopes there on top of Haleakala to look at the skies, and then another 5 years at Kirtland Air Force Base in New Mexico. And the thing that I realized is that the problem is very transdisciplinary. And what I mean by that is solutions can only come from the fusion of different disciplines, not just astrodynamics and physics, but social science and all these things. And then I said, what I want to be able to create, I can't create within the government for a variety of reasons, security classifications and these sorts of things. Where could I create something like this on the outside? And UT Austin is just the perfect place to do that, because not only does it have like a world-ranked, aerospace engineering program that has many world-ranked programs in public, public policy, government law, and the Odin Institute is very focused on solving problems that are either enabled or uniquely solved by using large-scale computing. And so I'm like, you know what? I'm not going to shy away from using computers and high-performance computing, and we have the Texas Advanced Computing Center that has like the 5th most powerful supercomputer on the face of the Earth, which is awesome. So all of these were like great reasons to come here, and so my center of gravity is Odin Institute, pun intended, because I wanted to bring in all these things under this massive computational framework.
Okay, and there's a lot of papers. You've written a lot of scientific papers, and I looked at a few, and my math goes up to about third-year statistics and a little bit of calculus. So it's like, wow, okay, this is really serious stuff. So let's begin with a basic question for our listeners and viewers who may not be aware of this. What's wrong with the current collision detection equations? Why are they so bad? I mean, isn't this stuff tracked already?
Yeah, so a couple of things. Thing number one is that all of the objects orbiting the planet right now operationally are modeled as cannonballs, as spheres. And I have to tell you that not many of them are spherical, actually. And so the thing is, the physics are already flawed. They're imperfect. And you might say, okay, well, how valid is this kind of cannonball model? And I would say, well, if you look at the current catalog that the Department of Defense maintains, about 26,000 objects, it seems like it's valid for about that, because that's the assumption that they make, right? So then the question is, if we're saying, well, we believe there's like 500,000 things up there that could be hazardous, but we only track 1% of that. Part of the reason why we're not tracking more is because of the flawed physics, okay? Because you can't predict, when I say tracking, what I really mean is you can detect an object and you can uniquely identify it. So we need to, so we need to detect it, and whenever I detect it, I need to say, yeah, that's Joey. I detected this, and it's Joey 1, 2, 3 or whatever. The inability to assign a first and last name to the objects pretty much means you can't track. And I would say our inability to develop a larger catalog in part is because of this, not being able to uniquely identify objects. So whenever things go into this collision, calculation, there's a couple of assumptions that, these things have, these relative speeds with respect to each other, and they have a time of closest approach, and that time of closest approach is known and is fairly certain, and that the uncertainty with regard to the relative position between things can be modeled as a Gaussian distribution, and that already is not perfect. And so, interestingly enough, and it's all couched under a probability, and within the realm of uncertainty quantification, typically uncertainty quantification breaks uncertainty into two different kind of groups: uncertainty that's driven by randomness, and then uncertainty that's driven by systematic effects. And the random part is called aleatory uncertainty, and it's also called irreducible uncertainty. So the thing is, you can't really know something better than its inherent randomness. If something is truly random, you can't really know it more than that because it's random, if it's truly random. But then this other part of the uncertainty, this systematic uncertainty, is called epistemic uncertainty, and that is reducible. That is basically, think of it as the reason you don't know it is because you're ignorant. And so by bringing different sensors and observations, how can you remove the ignorance so that in an ideal world, you end up with nothing but the inherent randomness? Like, that's your goal, is to reduce everything to its inherent randomness. And because we assume that all the uncertainty in collisions is random, if you actually scale the uncertainty and make it larger and larger and larger and larger, eventually the collision probability goes to zero. As the uncertainty becomes really, really large, the collision probability goes to zero. And then I ask people, does that make sense to anybody, that the more ignorant you are of the collision, that the less risky it is? Of course not. But that's part of the math, because it's assumed to be purely random, and it's not. In fact, a lot of these collisions or near misses, let's say conjunctions, have periodic effects. We put things in specific highways. The highways have intersections. We know about these intersections. So sometimes these conjunctions between any two objects, it's like, yeah, every 3 days these things conjunct just because of the relative geometries with each other. But so that's not random. That's actually systematic. And so I think just the math with which we represent the uncertainty and how we are modeling the physics, those flaws to me are the culprit of collision risks that are not properly quantified. And so I think the system generates a lot of so-called type 1 errors, which are false positives, which are telling people, oh, all the time you need to move out of the way because something bad's going to happen. And people become desensitized to, the sky is falling, Chicken Little kind of thing.
Right. And here we are, companies are going to be launching tens of thousands of CubeSats, which are rectangular, not cannonball shaped. So your physics is off. You're going to have tons of them up there. They all need to be spotted. So we've got a bunch of tools here, and you have a number of initiatives that you're promoting at the Odin Institute, and I want to go through them. So tools that listeners may not have heard of, there's optical fingerprinting, attitude observation, and the importance of simulation. And factors are acting on these things. There's solar and earth radiation pressure and Lorentz forces. And so one thing that you want to get into and make work better is something called photoacoustic sensing. And that is, let's define that. And how will you use it to improve RSO signature detection?
Yeah, so if somebody had to ask me, all right, man, so you want to lead this, world-class research program at UT Austin, in a sentence, what would you say you want to be known by? If somebody said they're the most awesome people at blank, like what would that be? And my answer is, we're going to be the world's best photon interpreters. That's what I want to be. And so a way to think about that is the following. People are familiar with fiber optics and know that light can carry information. And the way to think about this is the following. You have energy, light, photons, and all these different kind of wavelengths, not just visible, that interact with objects in space. And some of that energy is absorbed, but some of it is actually reflected and re-radiated by the object. And so what we're saying is the behavior of those photons is now changed. It's different because it's interacted with this object in space. And if I have a sensor that collects these photons that have interacted with anything in space, our group is going to be the world's best at interpreting the information carried by those photons to understand and characterize those objects in terms of size, shape, material properties, how the stuff is moving, all those sorts of things. And so specifically the photoacoustic stuff is, we've developed, with some technology from Japan, we've developed a photon counting device that can basically count photons at 50 million times a second. Okay, we can count photons at 50 million times a second. That's very rich. So we compress that to 50 kilohertz, 50,000 times a second. And basically the top end of the human auditory range goes to about 20 kilohertz. And so what we're thinking is the following. Alexander Graham Bell came up with this whole photoacoustic thing. It wasn't us. I tell people I never discover anything. I just use other people's stuff. And so basically he said, yeah, if there is some object that is vibrating and light scatters off of that object, the light scattering off of the object is now modulated by the object's vibration. And an example of that people can kind of maybe get their head around, and you can go to YouTube and find this stuff, is, there's a YouTube video of an empty potato chip bag in a room that's sealed, a sealed room, but had a window. And in that room, there is a stereo that's playing Mary Had a Little Lamb. So the stereo is playing Mary Had a Little Lamb, probably with the sound all the way turned up. And there's this empty potato chip bag that now is vibrating based on the Mary Had a Little Lamb thing. And there's a sensor outside the room that cannot hear whatsoever and only picks up the vibration of the potato chip bag. And based on the photons scattered off of that, basically interprets the photons as acoustic signals and can kind of, reconstruct Mary Had a Little Lamb. It's amazing. And so we're applying that to space objects. We're saying, again, back to the world's best photon interpreters, these objects in space are spinning, they're tumbling, they're vibrating, and now the photons reflected off of these objects are modulated by that. And if we can interpret those photons acoustically, maybe that provides us with an extra layer of knowledge about the makeup of these objects and what they are and how they're, and all these things. So that's the photoacoustic sensing piece.
Okay. So, and what you really want to be known for is that photon interpretation.
Absolutely.
And that is really interesting that you can recreate the original signal from the interpretation that you're getting. So we would like to use machine learning to identify things like threatening behaviors, or as a forensic tool after something crazy happens and you want to know what happened. But AI is still in its infancy. It's a big part of what we do here at Cold Star, machine learning, and we have data scientists and a connection with the local university. What do we need to learn how to do before we can make most use of AI in this application?
So for me, it's the following. For one, I'm trying to create a big data problem in SSA. We don't have that yet. And so a lot of the AI ML algorithms that we've used have not turned out to be meaningful because we still don't have a sufficiently large and diverse set of data. So when I say big data, you know, some people say, oh yeah, they're like, Moriba, I have this telescope and it has images that are like terabyte. So, you know, so I'm just going to send you a lot of these images and give you the big data problem. I said, no, that's called a lot of data problem, not a big data problem. And so big data is a lot of data that is disparate and very diverse. And so that's kind of what we're creating here at UT is this knowledge graph. It's a graph database, Neo4j, and we're trying to bring in all these disparate sources of information to apply AI and ML to the back end. But what we want to do, which we think will be meaningful, is to you know, use the graph database to link these disparate sources of information. But at the same time, we want to make it a physics-informed AI and ML. And so what I tell people is AI and ML inherently are stupid. They're not smart. And AI and ML tend to predict that tomorrow looks like today. And if your version of today is very limited, then the prediction of tomorrow is not going to be so good. So you want to feed AI and ML lots of todays, lots of different todays, and in that respect, then you'll get something meaningful out of that activity. So absolutely, I think that, and where I think it'll shine the most is in helping identify causality. But the thing is, you want to, human beings tend to think in very lower dimensional. And whenever you see information at a meeting or something, it's always two-dimensional, right? Plots. At most, you see a data cube or something. But it's like, well, what are all the dependencies on this stuff? What are all the other dimensions that you haven't been able to show for a variety of reasons? And really, you know, are there any causal relationships in the things that you haven't really tracked? And so that's what we're trying to do with, you know, crowdsourcing and amassing and making a big data problem for us to have in space, is that by linking all these things, then we want to say, okay, given this larger combined data set, there's going to be some mutual information in this data set with regards to some hidden parameters. And can AI and ML now discover these things? Can we go from data to discovery and not just look at correlations, but look at causality in that larger combined data set?
Okay, very cool. Hey, this is Jason Kanigan, the host of the Cold Star Project and the founder of Cold Star Technologies. I've decided to do something new. I've started doing daily update videos on who I met and what I learned the previous day in the space field. And it's a great sort of follow me thing. You can learn what I learn. I'm meeting a heck of a lot of people and learning a lot of things really fast. And the space field is really disparate. There are tons of nooks and crannies to go into and explore, from legal, operational, you know, regulatory, compliance, and gosh, the end customer. Who'd have thought about that, right? So you can sign up for this. If you go to coldstartech.com/MSB, that's short for Make Space Boring, the mission we're on, then you can sign up, and in your email you will get a daily notification that the new video has been posted. I'm also thinking about doing some branded mini courses and summarizing papers as I'm able to. So those will be some goodies that are in there as well. So if you're interested in that, go to coldstartech.com/MSB and join us on the mission to make space boring. Now back to the interview. We've kind of touched on this, but I want to specifically dig into it. There's a thing called credibility metrics, where is this valid? Does it really matter? And we kind of got into that in the last answer there. But what is missing with credibility metrics in terms of space situational awareness? Why do we need better credibility metrics here?
Yeah, so it's back to this uncertainty quantification and you know, the aleatory, random, and epistemic systematic. Here's the thing: I think one of the unique aspects of our research program here at UT and the Odin Institute is that, by and large, our approach is an abductive reasoning approach. And so I see many times that there's a lot of confirmation bias in the community, and people are very much intent on saying, yep, I want to specifically estimate this thing about the object, and they focus the algorithms on estimating that. And whenever there's incomplete information, then they fill that in with assumptions. So they're kind of extrapolating and trying to fill in these gaps arbitrarily. I'm trying to say, nope. If I had to create the perfect, Kalman filter, one of the things that Rudolf Kalman said back in the '60s, he got some award, and I'm paraphrasing here, but he said, you know, what I've done isn't the really awesome thing. The really awesome thing would be to develop a prejudice-free filter, prejudice-free, because we bias ourselves. And he said, and basically he said, I wonder how much the answer that my filter produces is basically biased on my initial assumptions, you know, and that's really what's driving the answer. So I take that to heart. I'm a firm believer in, I'm in this pursuit. The holy grail for me is this prejudice-free filter. And prejudice-free, you either get there by making zero assumptions or you assume everything. And so the abductive reasoning approach is to say, much in the way that a refrigerator actually cools something. So the refrigerator doesn't actually cool the thing, it actually removes heat, right? I want to remove ignorance. Our whole estimation program is not focused on it's not focused on actually estimating anything. It's more focused on the removal of ignorance removal system. And so the interesting thing is we use data to actually tell us what the wrong answer is so that we can remove the wrong answer. And so you have a family of things that survive, and all those hypotheses that survive are likely. You know, you don't know which one of those hypotheses is the true one because they all explain the evidence. As long as hypotheses can explain the evidence, don't leap outside of that to try to conclude something different. And so I think from the credibility perspective, what's missing in SSA is we tend to prematurely try to get to what the answer is, and we don't like, you know, 100 different hypotheses saying something. You know, General Many Stars wants to make a decision and just give me a green light or a red light on this. And it's like, well, I'm sorry, General Many Stars. Actually, given the evidence, it could be any of these things which are very different from each other. The message to you is you need to gather more evidence to further remove the wrong answer. So the collection of evidence should have as its purpose to remove ignorance. And that's the way we approach the problem here.
Okay. And it sounds like you're looking at more of an unsupervised learning approach than the supervised learning.
So we're trying to combine both a bit. Yeah.
I think Richard Feynman would be pretty happy with that approach there. Let's get into Bayesian equations. You mentioned the Kalman filter. You co-authored with another colleague a paper on something called the unscented Schmidt-Kalman filter, which I Googled and had a look at it. Wow, this is really in-depth in that. So tell us a little bit about that and Bayesian equations, how those Bayesian equations can be used to improve our space tracking data and models, and helping quantify that uncertainty, which is the main thing I think we're trying to accomplish.
Right. So one of the interesting things, you know, one of my prior postdocs, Manu Daland and this guy, Jeremy Hosono, they stumbled on these things called outer probability measures. And from just like probability measures begets probability density functions, outer probability measures beget these things called possibility functions, or a credibilistic approach. And so basically I'm going from the probabilistic world into more of a frequentist kind of mentality to these things to say, yeah, all the uncertainty, again, isn't driven just by randomness. It's driven by ignorance and systematic effects. the thing about Bayes' rule, and it's very powerful, and it's the workhorse, including like things like the unscented Schmidt common filter and stuff like that, is that they assume that you have a prior, you have some prior, some prior probability that you draw from. In the absence of if you have zero prior, the Bayes thing doesn't work. So that's the Achilles heel of Bayes, is you have to have some sort of prior to jumpstart the process. Given what we know about the physical universe, yeah, we can have some prior, but what we realize for SSA is that that prior is not complete.
Mm-hmm.
The prior is not complete, and so with outer probability measures and these possibility functions, we can actually use the same equations as Bayes, except that instead of constraining it to a probability, we're saying it's a possibility, meaning that give you an example with let's say a six-sided die. Let's say, for instance, you've had this since you were born, and you've been rolling this thing every day, and you just meet me on a train, and you know for a fact that it's actually fair, that because you've cast it 5 million times, you basically know, based on all the trials, that the probability of landing on any given face is 1/6. Me, I just assume that. In the absence of information, I'm just going to say, yep, I don't know any better, so I'm just going to assume it's like fair. Well, all of my uncertainty is really epistemic because it's based on its ignorance. Yours is completely aleatory because you've removed all the ignorance. You actually have gotten to the inherent randomness of the die itself. And so we've been able to see that we can actually use a lot of the Bayes equations in this possibilistic sense, but instead of saying, yep, we're just going to assume a probability and everything's random, we're saying part of it is the systematic stuff, and it allows us to work the math that way.
Okay. One of the things that you run into when you start looking at space situational awareness and what satellite is where, and that is a thing called ORCID. What is that, and how do you intend to use it?
Yeah, so back to this, I don't like making my own stuff. I like using other people's things. One of my roles in academia is to do things for community good, and I like the idea of open source software. And so ORCID is this open source astrodynamics software tool from this company CS out of France, and it's been demonstrated on a number of actual space missions. And yeah, I don't like reinventing wheels, and so all of our SSA algorithms and filtering implements ORCID. And where possible, wherever we see that there's some physics that we want to improve, then we just make direct contributions to ORCID in that sense.
Mm-hmm. And it's pretty neat. Yeah, it has that open source governance model, and I connected with a few people on that on that board of governors. So maybe one or two of them will be able to come on. We'll see.
There you go.
Yeah. All right. Well, let's jump into the next thing, which is modeling curved space. What's the deal with that? Why is that challenging about modeling RSO's travel through it?
So interestingly enough, I say motion of objects is kind of in two camps. There's gravitational, and then there's the everything else. From the gravitational perspective, that's kind of the curved space thing. So people can say, okay, well, you can call it gravity, but the Einsteinian kind of folks would say there's no such thing as this gravitational force. It's really a curvature of space-time. So from that perspective, we have good notions of how to model that space-time curvature. However, and we have parameters to correct Newtonian mechanics to account for this curvature of space-time. But the actual objects are on curvature of space-time manifolds that aren't exactly just based on these masses of objects, but are also influenced by, I'm going to call them real forces that are non-gravitational. And these are now all dependent on the physical characteristics of the object. So the curvature of space-time stuff, interestingly enough, the physical characteristics of the object itself, the debris or the satellite, they don't matter. They actually fall out of the equations of motion. All you have to tell me is where you're located. Give me kind of an initial position and velocity, where you're located with respect to these, the Earth and Moon and all these other masses, and I'll tell you what that curvature of space-time looks like. But the actual behavior of the object departs from that space-time curvature because of these photons that come from the sun, that heat objects up, that exchange momentum with the objects. These objects can be traveling in fields that passively collecting charge, charged particle environments, and they can get passively charged and then interact with the magnetic field, which can perturb their motion in ways that are not predictable exactly, the Lorentz force kind of stuff. So these are so we can model the curvature of space-time, but we have to have an and it's like, and these other things. But the real difficulty about the and is that they all depend on the physical characteristics of the object, which we don't have prior information about. So that's this huge inverse problem that we need to solve, is given observations, invert those observations to then discover the physical characteristics of the object that then help you better model the physics that depart from the typical, gravitational space-time curvature.
Okay. Let's hop into this final section here, which is debris field prediction, which is very interesting because, and you're going to have to define for me where this is useful, because you hear all these guys who say, okay, we're just going to launch small sats, CubeSats. They're going to be in orbit 3 to 5 years, and then they'll just burn up on reentry. And is that true, or do we need to be worrying about that? Or is this debris field prediction modeling that you're working on more for larger satellites?
So I would say this debris field, so a couple of things. One, looking at, like chicken and the egg kind of problems again. We're trying to develop the first scientific taxonomy for human-made objects in space. It doesn't exist. Again, all these things on orbit are modeled as cannonballs, as spheres. And I like to approach it from like a biological systems approach, which is to say, listen, a CubeSat in low Earth orbit is going to behave differently than a CubeSat in mid-Earth orbit and differently than a CubeSat at GEO. Even though it's the same CubeSat, let's say fabricated by the same person in the same way, if you could say, yeah, I'm going to clone this CubeSat as 3 things, and I'm going to put it in 3 different environments, the behavior is going to be different just from a habitat perspective. So can we understand what are the different orbital habitats, understand the environment of these habitats in terms of the fields, external fields, gravitational, charged particle, all these things, and then say, okay, now if we have different species of objects, rocket bodies, CubeSats, this sort of stuff, how are these things going to behave based on the type of object they are and the habitat that they reside in, much like animal populations and that sort of stuff. Nobody's developed that before. So that's one of the things that we want to be able to develop, and I think that's going to help inform us of how these individuals of these different species in these different habitats actually behave long term. What's the long-term evolution of these different species in these orbital habitats? Which ones are nomads? You might have some that, due to these perturbations, migrate from these low Earth orbits to these higher Earth orbits just due to these natural perturbations. But we don't know that exactly because we keep on modeling everything like it looks like a sphere and all this other stuff. So that's the thing that we're trying to get to. And the other thing too is that whenever I see these studies of, oh, that's going to re-enter in so many years and that sort of thing, the actual statistics that's brought into that to date, in my opinion, is extremely non-rigorous in the sense of, when I see a study, some people make an assumption on, let's say, the atmosphere model. Oh, so, yep, this thing's going to re-enter in 5 years. Well, what atmosphere model did you use? Oh, well, I used Jakia, Bowman, blah, blah, blah. Okay, so if you had to randomize the different atmosphere models, if you use MSIS 2000 or if you use just an exponential atmosphere, how does the answer change? And by how much and that sort of stuff? Like quantifying the sensitivity to the assumptions in the model, people don't do that because, oh, that's too hard. It takes too many computer nodes, that sort of stuff. we have high performance computing. We have tens of thousands of cores that could do this sort of stuff. They do it for other domains like plant genomics and all that stuff. They're not afraid of supercomputers, but for whatever reason, space people are afraid of supercomputers. I don't understand that. And so I think that's one of the hindrances that we're trying to remove, to say, no, we're going to embrace the complexity. And that's again, the reason I'm in Odin is to say, yeah, when we look at these debris fields, we're going to be able to start characterizing sensitivity to different assumptions in, different models and physics and all this other stuff, to give people kind of some bounds on, hey, the answer could be anything from 5 years to 100, depending on the model you use. Like, that would be good to know.
Right. So there seems to be a rush in the community to get right to, this is what it is, this is how it works, and it's way too early to do that. It's
ridiculous. Yeah, exactly.
Yeah. Wow. Well, this has been a lot of fun. I was talking to Fred Kennedy, former director of Space Development Agency, months ago, and I was asking him some questions about orbital collision detection and prevention and that. And he said, you need to talk to Dr. Moriba Jah, somebody who's actually out on the forefront of this stuff. And so I'm really glad he did that. And thank you for being here today.
Oh, thank you very much. It's an honor and a pleasure. And sorry it took this long. I've just been very busy. But I think the big takeaway from this is that with all the cool things I talked about, it's very clear that I'm not enough. So I'm not enough to solve this. And I'm really looking for collaboration and scaling this. So
okay, well, this is Dr. Moriba Jah. He is at the Odin Institute at the University of Texas at Austin. If somebody does want to collaborate and they've got that massive data or a good idea or whatever, and they want to connect with you, what's the best way to do that?
Yeah, just my name, Moriba at utexas.edu, and I'm easy to reach. I don't respond
right.
immediately, but I'm easy to reach for sure.
Right. Yeah, and I've deliberately held back because of reasons of time from asking follow-up questions in all these different areas, but it would be great to have you on again in a few months and maybe focus on one of these areas and really dig into it. So
I'd love to do that.
Thank you very much for being here.
All right, thank you.